Hi, my name is Cadence Gitline, and today I'll be doing a presentation on the decibel scale. This presentation is meant to be an informative presentation because in our curriculum we have not yet learned about the decibel scale, so I thought this would be really interesting for whoever may come across this video. For the history and background of the decibel scale, it was developed in the early 20th centuries by engineers at the Bell Telephone Laboratories to measure signal loss in telephone lines. Originally, they used the unit called the bell, named after Alexander Graham Bell, the inventor of the telephone. Because the bell was too large for practical use, they divided it by 10, creating the decibel. Over time, the decibel became the standard way to express sound intensity and signal strength, since it reflects how humans actually perceive changes in loudness on a logarithmic scale. Working with the decibel scale requires basic algebra skills and an understanding of logarithms. Since the decibel formula involves the comparing ratios using a logarithmic function, to work with the decibel scale, you need to be comfortable with scientific notation and calculator functions of logarithms. In more advanced uses like sound engineering or electronics, training in physics and signal processing helps you interpret what decibels values mean in real-world systems. One profession that I learned that relies on the decibel scale is an audio engineer. Audio engineers measure and control sound levels in recording studios, concerts, and broadcast environments. They use decibels to balance volume, prevent distortion, and protect the listener's hearings. Understanding how intensity changes on the logarithmic decibel scale helps them make precise adjustments and maintain high-quality audio production. On this piece of paper here, I have 3 different equations that I did have to go find a little help online how to solve because we have not yet learned about how to solve that. So for my first one here, I have comparing 2 sounds. A vacuum cleaner is 70 decibels and normal speech is 60 decibels. How many times more intense is the vacuum cleaner? So we have change in sound level, 70 minus 60 equals 10 decibels. The vacuum is 10 times more intense. Each 10 decibel increase is at 10 times more intense. For my second example, I have an everyday example. A quiet library is around 40 decibels and a busy classroom is 60 decibels. How many times more intense is the classroom sound? So we have 60 minus 40, which is equal to 20 decibels. Each 10 decibel is 10 times more intensity, so 10 times 10 would equal 100, and that would mean the classroom is 100 times more intense than the library. And for my last everyday example, I have listening to music through headphones at 90 decibels compared to a whisper is 30 decibels. How much more intense is the headphones? So we have 90 minus 30, which is equal to 60 decibels. So that would mean every 10 decibel increases equals 10 times more intensity. So we have 10 to the power of 6, which is 1,000,000 times more intense, which I thought was a little interesting because I'm a girl who likes to wear my headphones at probably too loud of a sound. And so I thought that was really interesting. If you were to listen to somebody whisper and then put your headphones on and play some really loud music that you like, that's a little crazy to me. And then on my paper here, I do have my sources that I will link also when I am turning in this presentation. And thank you for listening today on my presentation about the decibel scale.